Another thing that we can consider when we're finding the area between curves is that we don't necessarily need to do everything with respect to the x-axis. Okay, so we often just do everything with respect to the x-axis just because that's the way our coordinate system is set up, right? With x being the independent variable and y being the dependent variable. But for example, if we revisit the two functions that we had before of f of x equals x squared and g of x equals 2 minus x. Okay, so that looks something like this, right? More or less, and we found the area between the curves of this region over here and this region over here. And I briefly mentioned how to find the area of this part right here, right? And the way that we could find the area of this part right here was that we could integrate from 0 to 1 for x squared, and then add together that with the integral of 2 minus x from 1 to 2, right? Now, an alternative way to do it using this idea of area between curves is to look at this with respect to the y-axis. So we're like rotating it. I don't know. I don't think I can literally rotate on this, or I would. But we want to, if we were to rotate this 90 degrees and look at this as in terms of the y-axis instead of the x-axis as the reference point, then the 2 minus x part would be the larger part, right? And the x squared part would be the smaller part. And we could find the area between the two curves by taking the difference there, okay? So just like we're doing the top function minus the bottom function to find the area between two curves with respect to the x-axis, if we want to look at the y-axis as the reference point, we would do the rightmost function minus the leftmost function. So in order to do this, we need functions in terms of y. Okay, so a lot of the problems that you find, like when you're practicing this kind of thing, the problems will just be given to you in terms of y. But we can just take a functions that we already have in terms of x, and we can translate them into functions in terms of y, right? So we can just make this the square root of y equals x, right? You could also consider the negative square root of y, but we're only looking at the positive part anyway, the positive outputs. We're only looking between 0 and 2 specifically, so we don't need to consider that part. And then this is just going to be, 2 minus y, right? X equals 2 minus y. So basically the same function there. And then if we want to find their, we would need to find now the, the interval is from 0 to 2 on the x-axis, but we're looking at this in terms of the y-axis now, right? So the interval that we're going to be looking at is 0 to 1. So it's kind of like when you're doing a u substitution on an integral and you make the substitution and then you also have to change your bounds with the substitution for the definite integral, or at least that's one way to do it. Kind of the same idea here. We want to sub out the bounds. We want to look at, okay, our bounds with x is 0 to 2. So how does that translate to our bounds from y? Here we can see it pretty easily with the picture, right? But if we don't have the picture, we would want to look for this region specifically, we want to look at where the two functions intersect the x-axis. And then we also want to look at where they intersect each other. Right, so intersecting each other, we set them equal to each other. Where they intersect is where they are equal. And then we would solve that. You can do this with a substitution. Like you could let u equal the square root of y. So u squared is equal to y. I feel like we already did this on one of the problems. I think on this problem. But ultimately you'll end up with y equals 1. Right? And then this one right here, you'll end up with y equals 2. And then this one over here, you'll end up with y equals 0. Okay. Now, we only really need that intersection point because of the area that we're finding. We just need to do the integral from 0 to 1. Okay, so now the way we're integrating is going from here to here on the y-axis, right? And on that part, the 2 minus x is larger than the x squared. So we're going to do the integral from 0 to 1 of 2 minus x minus x squared. Or I'm sorry, we're doing this in terms of y, not x, right? So this is going to be 2 minus y minus the square root of y dy instead of dx. Okay. And then everything just follows as normal at that point. It's really just the setup that can be a little bit different. And now we're just doing the same thing with a different variable. So we get 2y minus y squared over 2 minus 2/3 x to the 3 halves, y equals 0 to y equals 1. Okay, and this should have been y. See, I'm just so used to doing everything in terms of x that it's easy to just write down an x. So we get 2 minus 1/2 minus 2/3, and then everything else will be 0, right? So then you can simplify this. You should get 5/6 here, okay? So to recap, we are looking for the intersection point of the two functions, and then we're doing the rightmost function minus the leftmost function, okay? So let's do another one without drawing the picture, just so we can kind of get a sense for how we're going to do this algebraically, because sometimes it's, maybe it's a tricky picture to draw, or maybe it's hard to get it exactly right. We don't always want to rely on a hand-drawn graph, right? Because, it's just not reliable necessarily. So we want to be able to back it up algebraically. So let's try another one here. Okay, so this one is, this example I found here, it's a bit tricky. So let's try this one. Okay, so this one wants us to find the area that's enclosed by the functions x equals 2y and x equals y cubed minus y. Okay, so specifically the part that's enclosed, meaning that we really just need to find the intersection points, and we're finding the area between all of the intersection points. Okay. So enclosed means that it has some kind of bounds, right? So it's bounded by these intersection points. Okay. So we're not cutting it off arbitrarily at like a different point with like an imaginary line like we would sometimes. So first step is to find the intersection points. Okay, so to do that, again, we'll just set the functions equal to each other. So 2y equals y cubed minus y. And then we're going to solve this. So we get y cubed minus 3y equals 0, which implies that we have y times y squared minus 3 equals 0. So y equals 0, or y squared equals 3, meaning that y equals plus or minus root 3. So there's 3 intersection points, okay? So we can imagine that we're going to have an integral from negative root 3 to 0, and then another one from 0 to root 3. So now the question is, which one is the larger one, right? So like ultimately we could just do one big integral with the absolute value of these two, right? And then it doesn't matter which one is larger. Okay. So we could write it like this, and this is mathematically correct, and this is what we're doing. But to actually solve this now, we need to figure out which one is larger than the other and on which of these intervals, with the intervals being negative root 3 to 0 and 0 to root 3. So we essentially need to solve this as an inequality of where is 2y greater than y cubed minus y. Okay. So we can solve it like we would any polynomial inequality. Then we already found the zeros. So it's easier to bring it to the this side over here, because this is already how we had it. This is going to be less than 0. So we'll do a sign chart here with 0, root 3, negative root 3. And then we can plug in whatever numbers here. So we can plug in 1, for example. If we plug in 1 to this, we have 1 minus 3, so that's negative. If we plug in negative 1, we have negative 1 minus a negative root 3, so that's going to be positive. If we plug in, say, 2, this is 8 minus 6, so positive. And if we plug in negative 2, we have negative 8 plus 6, which is negative. Okay. So we're only actually interested in the part between negative root 3 and root 3, so we don't need the entire sign chart. But we can see that negative root 3 to 0, this is positive, implying that this first inequality is like false, right? So this implies that the y cubed minus y is greater than 2y. Okay, so maybe a good idea to write this down. So here, y cubed minus y is greater than 2y. And then in this part, this is negative, implying that the inequality was correct. So here, 2y is greater than y cubed minus y. Okay. So now we have it broken down so that we can solve the integral. Okay, so we'll have the integral from negative root 3 to 0 of y cubed minus y minus 2y dy. And then the integral from 0 to root 3 of 2y minus y cubed plus y dy. And now we'll just go ahead and evaluate this. We have y to the 4th over 4 minus y squared over y minus y squared from y equals negative root 3 to y equals 0. So we should get some cancellation here, hopefully. Plus y squared minus y to the 4th over 4 plus y squared over 2 from y equals 0 to y equals root 3. Okay. So the 0 terms are all just going to be 0, so we don't have to worry about those. This is going to end up being root 3 to the 4th over 4 minus, which we could just simplify this actually. That's going to be 9, right? Because you square it once to get rid of the root. So you have 3, and then you square it again, and you'll be at 9. Minus negative root 3 squared is going to be 3. I don't know why I wrote over y here. This should have been over 2. And then minus, again, 3. And then over here we have plus 3 minus oh, I'm sorry. This one, these all should have been negative, right? Because I skipped over the 0 bound because that's 0, but it would have been 0 minus all of this stuff, right? Because this is the lower bound. So this should have been negative 9/4 plus 3/2 plus 3, because we'd be subtracting them all. Okay. So now this one, we're doing the top bound. So these are all going to be positive. So root 3 squares is 3 minus, again, 9/4 plus 3/2. Okay. So we essentially just get the same thing for all of these. So we get just 2 times all of this, basically. So 2 times 3 plus 3/2 minus 9/4. Right, so 6 plus 3 minus 9/2 it looks like. So then we'll have 9 minus 9 halves, which will also be 9 halves. Okay. And that would be our final answer.